In this tutorial, we will introduce the concept of conditional probability, and we will do that using an example. So when we go through this example, from time to time the arithmetic might get a little involved, but don't let that intimidate you. The concept of conditional probability is quite simple, really. Just that the calculations can get a little tedious sometimes. So let's introduce this with a context here. So the scenario that we have here is we have a police area, police precinct, if you will, or police district. And over the course of last several years, 1,200 police officers have applied for promotion. Okay? And what this table gives you is the breakdown of who got promoted, who didn't get promoted, and by gender. Okay, so let's first understand the numbers that are being shown, then we will get to probability. So we have a total of 1,200 officers who applied for promotion. So that's your sample space. Remember the concept of a sample space that we introduced when we just started talking about probability. So what we are saying here is out of these 1,200 officers who applied for promotion, 960 were men. So this column is men, and you can see this total says 960. So out of the 1,200, 960 were men, 240 were women. So if you add those two together, you get 1,200. On the other side, if you look in the other dimension, so this is by gender. This is the breakdown of the 1,200 officers by gender. 960 were men, 240 were women. Now, if we break down the 1,200 by who was promoted and who didn't get promoted, regardless of gender, then we are saying that out of those 1,200 officers, 876 did not get promoted, regardless of gender. And 324 did get promoted, again, regardless of gender. Okay? So, all right. So, let's say what is the first probability question. So if I picked an officer at random from this sample space, what is the probability? Oops, let me change the. What is the probability of being promoted? Let's say P means promoted, that the officer got promoted. What's the probability? So I pick an officer at random. What is the probability that they got promoted? So remember the definition that we had in our previous tutorials. The probability of an event is equal to the number of outcomes in that event divided by the number of outcomes in the sample space, assuming that all outcomes are equally likely. So out of these 1,200 officers, 324 were promoted, right? So if I pick an officer at random, the probability that the officer is promoted is simply 324 divided by 1,200. So that's the probability of being promoted. If I pick an officer at random, the probability of being promoted is 0.27. So obviously the probability of not being promoted, NP means not promoted, would be 1 minus 0.27. Okay, is equal to 1 minus 0.27, which is 0.73. I can confirm this in another way. The probability of not being promoted, 876 didn't get promoted, right? So out of the 1,200, 876 did not get promoted. So the probability of not being promoted is 876 divided by 1,200, and you see that to be 0.73. So everything lines up, it matches, okay? So now let's look at it again, another dimension. So this is by breakdown by promoted and not promoted. So suppose I pick an officer at random out of this 1,200. What is the likelihood that the officer is male? Okay, so the probability of being male. So out of these 1,200 officers, 960 are men, isn't it? So this probability is equal to 960 divided by 1,200. That's the probability of an officer being male. An officer being picked at random being male is 0.8. Okay. Similarly, the probability that I pick an officer at random and that the officer is female, this is obviously equal to 1 minus 0.8 is 0.2, but I can confirm it in a slightly different way. This is equal to, out of those 1200, 240 are women. You can see here the total is 240. So this is equal to 240 divided by 1200. It's the same 0.2. Okay, so everything lines up now. We got the probabilities of being promoted and by gender. Okay. Now, so far we haven't looked at these inside numbers. Okay. First thing you can see, I'll add these four numbers. I'll just add these four numbers, and you will see that they will add up to 1200. They'll add up to this total over here, 1200. So right off the bat, you can see that these numbers in the middle, they give you the breakdown of these 1200 both by gender and by status of promotion. So how do I interpret the number? How do I interpret 228? 228 is the number of officers who were men and who got promoted. So there are two things happening at the same time. Similarly, 36 is there are 36 officers who were women and who got promoted. So these are what are called joint probabilities. So let's take each of these numbers. Just like see in all these four numbers, we divided by 1200. That was the denominator, isn't it? So let's do the same over here. So I will take 288 divided by 1200 and I get a probability. I take 36 and I divide that by 1200, and I do the same for the remaining two here. 672 divided by 1200. Notice in all four cases that I'm doing, the denominator is 1200. It's equal to 204 divided by 1200. Now if I add these four numbers up, just like these four added up to 1200, so if I add these four up, they should add up to 1. So let's do that. Do you see it added up to 1, as I would expect, right? So now let's calculate some other probabilities. We know what 324 divided by 1200 was the probability of being promoted. So it's equal to 324 divided by 1200. Do you see this 0.27 is what we had gotten here? This is the probability of being promoted regardless of gender. Right. Same thing over here. 876 divided by 1200 is 0.73. And if I add these two numbers, this plus this, it should add to 1. Okay. Similarly, if I come to break down by gender, 960 divided by 1200 is 0.8, and 240 divided by 1200 is 0.2. So if you add 0.8 and 0.2, you get 1. All right. So let me now color code the probabilities on the sides next to the total. So let me shade that in yellow. These four probabilities are what are called marginal probabilities because they are being computed at the margins of the table. Okay. So we know what these two numbers represent now. 0.8, 0.2 we have calculated here. Okay. 0.27, 0.73 we have calculated over here. Okay. Now the probabilities in the middle here, these are what are called joint probabilities. So I explained that in a couple of minutes back, but let me shade this in a slightly different color. I'll make it orange. So this 0.24, this is the probability of being promoted, and you remember the union intersection difference of events, the probability of being promoted and, so let me get the and symbol here, and being male. So being promoted and being male. This is equal to 0.24. So this is a joint probability. Similarly, if I take the 0.17, what is it the probability of? It is the probability of being not promoted, NP, and the officer being female. So this is 0.17 is at the intersection of not promoted and women. Okay. So this is equal to 0.17. So these two probabilities, 0.24 and 0.17, these are what are called joint probabilities. So there are two events involved, and you want to know what is the likelihood of those two events happening together. One event is not promoted, the other event is the officer is a woman. So I pick an officer at random, the officer is not promoted, and the officer is a woman. That probability is 0.17. Okay, now we have laid the groundwork for our conditional probability, and we come back to our original question: is there evidence of gender bias? Okay, now if you knew nothing about conditional probability, a very intuitive way in which you would answer this question, is there evidence of gender bias? The way I would look at it is, okay, there are 960 men, out of which 288 got promoted. All right, so let me compute that probability. 288 got promoted out of 960 men. So that probability is 0.3. Let me center it. Okay. Now let me compute the other one, the same thing for women. So there are only 240 women and 36 of them got promoted. So the likelihood is 36 divided by 240. So now when I compare these two are also probabilities, but these are what are called conditional probabilities. So how do I interpret it in words? What is this 0.3 the probability of? It is the probability of being promoted given that the officer is a male. So once I pick a male officer, so I do pick at random, but I don't pick any officer at random. I pick a male officer. Out of the 960 male officers, I pick an officer at random. What is the likelihood that they were promoted? Then that probability is 288 divided by 960. Okay, so this is what's called a conditional probability, and the way you write it is probability. The symbol is slightly different. So do you see over here it is probability of being promoted and male. So this is the probability of being promoted given that it's a male. Okay. So I'll move this 0.15 here, 0. Let me calculate that. It's 36 divided by 240. Okay, so here this is the probability of being promoted given that the officer is female. Okay, so let's compute some other probabilities. The probability of being not promoted given that the officer is male. So once I tell you the officer, I'm picking an officer, but not out of the 1200 in total, but only out of the men. So I pick a male officer at random. That means my denominator immediately becomes 960, not 1200. Okay, so once I tell you given that it's male, the denominator has changed to 960, and out of those 960, 672 did not get promoted. So the probability of not being promoted given that the officer is a male, this is equal to 672 divided by 960, okay, which is 0.7. So now let's do it for the women. So probability of not being promoted given that the officer is female. So I'm telling you it's a female officer. There's nothing uncertain about the gender of the officer. So I don't pick from the 1200, I pick from the 240 officers who are women. And out of that, the probability of not being promoted is 204 divided by 240. So it's equal to 204 divided by 240. Okay, it's 0.85. So these are conditional probabilities. So make sure to, as we go through this discussion, try and understand the distinction between conditional probability and joint probabilities. Okay, so let me write that down. Try and understand the distinction between the two. Both involve two events. Okay, so let's pick one, P M. So here are two events. One event is that the officer is promoted. So let me put it in different boxes. P, and this is M. Sorry, M. So there are, in both cases, in both joint and conditional probability, there are two events involved. In our case, this is P and M. P is the officer is promoted. M is the officer is male. Okay. What is the difference between conditional and joint? When you're computing a joint probability, both the events are unknown, they're uncertain. Okay, so you're saying I pick an officer at random. What is the likelihood that the officer is male and the officer is promoted? So both those two events are uncertain, and that's the probability that was calculated here is 0.24. The denominator was 1200. So if I pick an officer at random, I don't know their gender and I don't know whether or not they were promoted, then of course I'm looking at all 1200 officers. So the denominator is 1200, okay, and male and promoted is 288. So 288 divided by 1200 is what gives you the 0.24. Now when you come to conditional probability, probability of being promoted given that it's a male, as soon as I tell you that it's given a male, then out of those two events, one event has occurred for sure. You know that the officer is, you know the gender of the officer, it's male. And as soon as I tell you that the officer is male, then your denominator no longer is 1200, it's 960. And that's how we ended up getting the 0.3. Okay, so I hope you can see the conceptually what's the difference between conditional and joint probability. Okay, so now let's parse this 0.3 a little bit further. So if I look at this table now, not look at the raw numbers but the probability table over here, then how can I come up with the 0.3? So I'm going to do a calculation over here, is 0.24 divided by 0.8. Do you see it's also exactly 0.3? This, let me shade it in a different color, green and green. Do you see these two colors are the same? So I've gotten the same result. So how did I get this 0.3? I divided 0.24 by 0.8. And what is 0.24? Is the probability of men and promoted, and 0.8 is the probability of men. So this guy, 0.3, the way I calculated it is probability of being promoted and male. That was your 0.24. That's this guy, divided by probability of this 0.8 is probability of being male. Okay, let me widen this a little bit. That's how I got my 0.3. Okay, therefore probability of P given M is equal to, so this is the conditional probability expression, the way you compute conditional probabilities. So probability of P given M is equal to the probability of P and M divided by the probability of M. So that's the numerical calculation. As I remember, I told you a little while back that the arithmetic can get a little involved, but don't let the arithmetic get in the way of understanding. I hope you understood the difference between conditional and joint probability. Both involve two events, but the in one case, in the case of conditional probability, one of the events, the one that is given, that has happened for sure. Okay, whereas in the case of joint probability, both events are uncertain. Okay, now that we have introduced the concept of conditional probability, then I will end this tutorial by introducing a very important concept, and that is the concept of independent events. Okay. So again, if you have two events A and B, if you have two events A and B, when do we say that they're independent? We say that they're independent when the probability of A given B is equal to the probability of A. Okay, so just in common sense or in layman's terms, what is this telling you? So look on the left hand side and look on the right hand side. Left hand side is saying the probability of event A given that event B has happened. So somehow you're thinking that the two are related, that if B has occurred, it somehow has an effect on A. It's a probability of A given B. On the right hand side, it says only probability of A. You don't see any B on that side, correct? So if these two are equal, what we're saying is B has no effect on A. So probability of A given B is the same as the probability of A. If this is true, then we say that A and B are independent, and we would check this by calculating it. Okay, so let's do our calculation over here. We'll say this is an original question. Remember, is there evidence of gender bias? So this is how we would ask the question in plain English. If we translate that to probability, what we are saying is P and W independent? Meaning, here are two events. One is the officer is promoted. The other event is the officer is a woman. Are those two events independent? Meaning, if W has happened, does it have an impact on P? Okay, or it doesn't? We want to check it. So we'll simply have to check this condition. So what we need to check is the probability of P given W is it equal to probability of being promoted? So this is what we have to check. If these two are equal, then it's independent. Then we say the two events are independent, that is, gender has no effect on being promoted. But if the two are not equal, then we say yes, being promoted and being a woman, they're related, they're correlated, and gender is not independent of being promoted, or rather being promoted is not independent of gender. Okay, so let's do the calculation. Probability of being promoted, we had done this before. I don't want to repeat the calculation. This is 0.27. We had already done that calculation here. That if I don't give you any gender, independent of gender, the probability of being promoted is 0.27. What is the probability of P given W? You see, it's the calculation that we had done. If I tell you the officer is a woman, the probability of being promoted is 0.15. The probability of being promoted, given that it's a woman, is 0.15. So this left hand side is 0.15. So these two are not equal, isn't it? Let me see if I can find the symbol for not equal to. let me try and see if I can find it. Here we go. Is not equal to. So 0.15 is not equal to 0.27. So gender and promotion are not independent. Okay, so this is the concept of independent events. And when two events, if they turn out to be independent, so if A and B are independent, then probability of A and B, the likelihood of the two of them occurring at the same time, probability of A and B is equal to the probability of A multiplied by the probability of B. Okay, so this is the famous multiplication rule of independent events. So let me boldface this. Okay, so if I tell you that two events, or somehow you know because of the way the problem is set up, if you know that two events A and B are independent, then the likelihood of those two events happening together, the probability of A and B, is equal to probability of A multiplied by the probability of B. And that follows from this definition of what constitutes independent events. Okay, so this concept of independence is very important. We will see it later on when we get into some discrete distributions. This concept is very important. It arises a fair amount in practice, and it's used to compute probabilities of various outcomes. So we will work more problems like this and get more practice with conditional probability and independent events in class.